All right, let's get right into this explainer. Welcome. Today, we are looking at the ultimate head-to-head battle of how things break. We're going to explore exactly what the stress-strain curve reveals about material survival and uncover why the objects around us behave the way they do when pushed to their absolute limits.
So think about this for a second. Would you rather a bridge bend like a giant piece of taffy or completely shatter like glass? I know, it sounds like an extreme choice, but this is the exact stark contrast in mechanical behaviors that engineers have to consider every single day. So today, we are going to compare ductile and brittle materials using some really simple analogies to explain their highly unique mechanical behaviors.
Let's start with Section 1, the invisible forces, understanding the push and pull.
To understand how things break, we first have to understand the invisible forces acting on them. First up, we have stress. And think of stress as the literal internal push or pull on a material's atoms. If you've ever pulled your hands apart as hard as you possibly can against a tightly wound rubber band, you've felt this intense force. Now, in engineering, stress isn't directly measured. It's calculated as the applied force acting on a unit area of the material's cross-section. We typically measure this in megapascals, or MPa. Basically, it's the root cause of everything that is about to happen to our material.
Which brings us to the flip side of the coin, strain. If stress is the invisible force, well, strain is the physical reaction to it. It's basically just how much the object stretches or squishes in response to all that stress. And because it simply measures the change in length relative to the original length, it's completely dimensionless, no units at all. We usually just express it as a percentage of elongation. Moving on to Section 2, mapping the breaking point, reading the stress-strain curve.
All right, now that we know our forces, we need a map. And this curve is generated by a standardized test, like the ASTM E8 tensile test, where a machine literally pulls a piece of metal apart. As the tension builds, the material travels through 5 distinct regions. First, the proportional limit, where stress and strain rise together in a perfectly straight line. Then, the elastic limit. This is absolutely crucial. It's the point of no return. Cross this, and the material is never snapping back to its original shape. Next up is the yield point, where permanent plastic deformation begins. The tension keeps building and building until we hit the ultimate tensile strength, which is the absolute peak stress the material can handle. Finally, the whole thing ends at the fracture point, where the material physically separates.
So from this test data, engineers can extract some highly essential mechanical properties. The slope of that initial straight line, that gives us Young's modulus, which is the material stiffness. The peak of the curve gives us the ultimate tensile strength. But here's a really fascinating detail for you. Many metals, like aluminum alloys or stainless steel, they don't actually show a sharp, obvious yield point. They don't just suddenly give way. So engineers use this clever workaround called the 0.2% offset yield strength. They basically draw a parallel line starting at 0.2% strain just to find a standardized, practical point where that permanent plastic deformation kicks in.
That brings us to Section 3, the ductile taffy, the long road to failure.
So, how do different materials actually behave on this map? Let's dive deep into the personality of our first category, ductile materials. I want you to picture stretching a piece of taffy, or maybe a really thick wad of chewing gum. A ductile material, like mild steel, aluminum, or copper, is remarkably forgiving. It shows extensive plastic deformation before it breaks. It graciously warns you before it fails. As it reaches its limit, it begins necking, this localized, highly visible shrinking of its cross-section. It's exactly like when you pull taffy apart and it gets super thin in the middle right before it separates.
Just look at this number. Ductile materials can typically achieve an elongation at fracture of 15 to 40%. That is an incredibly impressive stretch. They are absorbing massive amounts of energy, extending way beyond their original length before they finally decide to give up. But all this extreme stretching creates a bit of a quirk in our data. On a standard curve, we plot engineering stress, which calculates stress based on the original thickness of the material. And because of that, the curve actually dips downward during necking, making it look like the material is somehow getting weaker. But that's an illusion. If we plot true stress, which accounts for the continuously thinning neck of the material, the curve goes up and up. The actual localized stress on our stretching taffy is rising relentlessly until the very end. All right, let's flip the script. Section 4, the brittle cracker. Sudden and catastrophic. Let's focus on the exact opposite extreme. Forget the taffy for a minute. Think about snapping a dry cracker right in half. Brittle materials, like cast iron, hardened steel, or ceramics, have a totally different personality. They fracture very close to their elastic limit. Their crystal structures simply do not allow their atoms to slide past one another and bend. Because of this, they absorb very little energy. There is negligible plastic deformation, and, honestly, most terrifyingly, there is absolutely no visual warning. They just shatter abruptly. You can clearly see this difference in the literal aftermath of the destruction. If you look at the physical pieces of a tested ductile specimen, the fracture face looks fibrous, often forming this distinct cup and cone shape where it finally tore apart. But look at a brittle fracture, it's flat, it's granular, and it looks highly crystalline. It didn't tear, it just snapped.
So putting our taffy and crackers side by side translates these analogies perfectly back into the hard analytical data that engineers rely on. Ductile materials give us extensive deformation, high elongation, usually over 5%, and very high toughness. Brittle materials, on the other hand, give us negligible deformation, less than 1 or 2% elongation, and very, very low toughness.
Which leads us to our final part, Section 5, Real-World Survival. Why toughness matters.
Let's connect all of this back to the real world. Why does this head-to-head comparison matter so much outside of a testing lab? Because, plain and simple, human safety depends on it. The crucial point here is the modulus of toughness. Mathematically, this is the total area under the stress-strain curve up to the point of fracture. It represents the actual energy a material can absorb before breaking. That massive, wide area mapped underneath our ductile taffy curve translates directly to high toughness. A brittle material might be very strong and peak really high on the graph, but because it doesn't stretch, the area under its curve is tiny. It just can't absorb impact. Because of this, ductile materials are heavily preferred for things like pressure vessels, bridges, and buildings. Engineers intentionally choose ductile metals for structures subjected to dynamic loads. Why? Well, because if something goes wrong, say a massive truck drives over a bridge, the bridge will visibly sag, permanently deforming to absorb that energy. It gives everyone a loud, clear, visual warning to get away long before it ever actually collapses. A brittle structure would just suddenly vanish right beneath your feet. And these exact stress-strain principles directly drive the rigorous safety codes used in global manufacturing. The properties we've been talking about dictate the allowable stress values in ASME Section 8 for pressure vessels, they ensure welders are fully qualified under ASME Section 9, and they require standardized testing through ASTM E8. The curve isn't just a theory, it is the fundamental rulebook that keeps industrial equipment from failing catastrophically. So, I'm going to leave you with this thought. Take a quick look around your room right now. Based on everything we've covered, which objects around you would graciously bend like taffy under pressure, giving you a warning, and which ones would just snap suddenly like a cracker? Understanding the invisible mechanical behaviors hidden inside every object completely changes the way you look at the engineered world. Keep exploring, and I'll catch you in the next explainer.